Alright, yeah. Hey y'all, we live. Alright, welcome to Sunday Night Live, KP edition. We're going to what's this thing? Combinational circuits. Alright, if you're in the chat, thumbs up. Okay, smiley face, whatever you want to put. That way, yeah. I know you're there. I feel like I have an audience. If I have an audience, smile. Oh, I really don't smile that much, but you know. Alright, it is Sunday Night Live. Remember, there are classes for Cape. How do Cape classes go? All Cape classes are usually online. You can message me on Instagram or you could WhatsApp that number. Computer science right now for upper 6 is on Tuesday night, lower 6 is Thursday afternoon. Upper 6 is Wednesday night for IT and Tuesday afternoon for lower 6. And yeah, Instagram is where the mission goes. Every Friday I choose what topic I'm going to do, so I put up on Instagram what topic I want to do, and somebody said I suggested logic gates, and somebody said so. Every Sunday night 9 to 10 inside live. So let's go. Combinational circuits. Anybody? Ugh. Say hi in the chat. Wave. Yeah, wave. That was kind of good. Right. Hey, Kimberly. All right, let's go. All right, so for combinational circuits, what happens is you have to understand that there are different logic gates. It's really not too hard to understand. I think they do this in physics or something. So there's an AND gate, there's an OR gate, and there's a NOT gate. AND means that both of them must be true for you to get an output that is true. So it doesn't matter what any other one of them has, but both of them had to be true. That's an AND. It's symbolized by a nice curve. OR, which is kind of not like a curve, it's kind of pointed, but not pointed like a triangle. OR means either or, one of the two. So once there's a 1 anywhere, you'll get 1 as an output. Whereas if you have 2 zeros, you'll just get nothing. That's OR. And then there is not. Not means whatever comes in, you'll get the opposite of that coming out. So if a 0 comes in, you'll get a 1 coming out. If you get a 1 coming out. That's the easy part. There's not really much to worry about there. Equations for the gates now is called Boolean Algebra. So it works something like this. If you want to say AND and is basically multiply, or is basically add in terms of the sign, right? And not is basically some sort of opposite. So not, it could represent with this little kind of thingy there, or it could represent it with a little tilde thingy there. One of the two. So if we had to represent a circuit and we have an OR gate, we have to multiply. We could also use this symbol, or sometimes you see A dot. You could also use this symbol, which is look like a V, or it'll just be A plus. Those are the symbols that they tend to use. So when you're doing an equation, the easiest thing to do with the equation is to work backwards. Why? Because you'll be able to build the equation easily. So if this is a AND gate, that means we have a plus sign in the middle, right? Then we deal with what is on the left side of the plus sign, which is a OR gate. So that means we have something multiplied by something, and the thing that is multiplied is B and A, and then it's going to reach the OR gate, which is the plus. So now we dealt with this side, so now let's deal with what goes on this side, which is not A and sorry, but all the cars passing there, but you know, I don't know, people important this sort of thing. Right, so what we basically have is a B not A and then a not A, and that's a truth table there. I mean, that's our equation, but notice I work backwards. So I got the plus first, then I got what is on the left side, and then I got what is on the right side. And if you do that for any equation I ever get in any past paper or anything like that, it will always work that same way. So now let's do the truth table fit now. Truth table has a B, a A and a B, and then we have B and A, and then we have not A, and then we have the last equation, which is B not A plus B A plus not A. Right, good. So whenever you have a truth table, you're gonna start off with always 0 0 0 1 1 0 1 1 are always your possible inputs. So when you get 0 0, right, good. So now we're going with B and A. So B or A, sorry, B and A. So B and A is going to be 0 for the 0, 0 for that there, 0 for that there, and 1 for that there. Then we're going to go with the not A, which is going to be whatever A is, the opposite of A, so it's going to be 1 1 0 0. And now we're going to go with B and A, or A or not A, which is just basically going to OR these two. So you're gonna get 0 0 0 0. Kind of weird, but hey, sometimes that's how the operators go. Any questions so far? Or do you want a harder equation to work out? Did I work that out correct? I think so. Yeah. Yeah. Oh shucks, my bad. There's a OR here, so it's supposed to be 1 1 0 1. Yeah. I fixed it. I fixed it. Alright, so good. Fix our problem, so we should be good there. That is how you do equation and a truth table. Trust me, once you do the diagram backwards, you will always get the right equation, and then the truth table will just be a matter of you remembering this stuff here. Good. Moving on. Alright, so then you have these special logic gates now, which will be inverted logic gates, which will be NAND, which is a NOT at the end of a AND. They could have done this, but I don't know. They thought they didn't have enough paper to draw diagrams like that, so NAND. So basically, the NAND or not AND will be the opposite of what you would get from a AND. So in a AND, you'll normally get 0, 0, 0, 1. Or in a NAND, you'll get 1, 1, 1, 0. And the opposite of a NOR, where you'll get 1, 0, 0, 0, you'll get the opposite of that. So where you get 0, 1, 1, 1, 1, you're now going to get 1, 0, 0, 0. Right? So the opposite of them, just invert whatever the output is supposed to be. That'll be an AND. Right. Now, they have AND and NAND and NOR and whatnot, but then they needed some special types of gate, which is an exclusive OR. There's exclusive OR and there's exclusive NOR, and then all sorts of other exclusivities that will happen, but the one that the syllabus has is exclusive OR, right? Exclusive OR means that you will only deal with the ones that have a 1 and a 0, or a 0 and a 1, and you will leave out the ones that are the same. Where this comes in life is that in some circuits, you'll just want these two conditions to give you a 1, not this one, depending on the type of circuit. But that's basically just how the CPU works. So we're not going to be speak up too much about that, right? And the diagram for exclusive OR is pretty simple. You could cram it off, because cramming it off is what makes it easier. Because even though you understand it, you still have to remember it. So exclusive OR is represented by a plus and a circle inside of it, so that's exclusive OR. And it's made up of a OR, and two NOTs. So all you have to remember is draw the diagram OR and NOT and NOT, and then just make sure the two ORs go into the two ANDs go into the OR, and then one NOT go there, one NOT go there, and then one gets the A and not B, and one gets a B and not A. And this diagram here is pretty easy to remember. Sometimes they ask you to draw it, sometimes they don't, but that's okay. So what's the point of logic gates? The whole point of a logic gate is that you want to route electricity, right? But then in the age of computing, when they created computers and they were starting to experiment with storage, they started to things like flip-flops. So what a flip-flop does is it's a digital circuit that has two stable states. Now, when you think of two stable states, you think of 1 and 0. What's the basis of how a computer talks? 1s and 0s. So when you have a flip-flop, you can either let it hold a 1 or you can let it hold a 0, and it will serve as 1 bit of memory. So because a flip-flop holds 1 bit of memory, if you bunch a whole set of flip-flops together, you could end up getting 4 bits of memory, and that will give you the ability to store numbers now. And once you could store numbers, then you could talk to a computer. And that is the whole point of a flip-flop. It's the ability to store information for future use. And it's using like registers, memory. Well, yeah, memory is actually transistors, but flip-flops for registers. Basically in the CPU. Right, that's where flip-flops are used most of the time. Okay. So, according to the syllabus, you have 3 types of flip-flops to use: a JK flip-flop, a T flip-flop, and a RS flip-flop. You don't need to know like every single thing about them. You basically just need to know the box diagram, but I will show you how it actually works. Just for you to understand. A RS flip-flop is known as a reset or set reset flip-flop, right? So set is for S, reset is for R. Yeah, that's the characteristic of a flip-flop here, functional flip-flop. Good. Okay, so now moving on, those are the characteristics of a flip-flop. Right, so now the RS flip-flop, it has two options, set or reset. When you send no input to the reset or set, which is the input part of it, you get no change, right? Wherever the state is, that's where it will stick to, right? It will stay at its present state. If you send 1 to the set, you're going to get Q is equal to 1, which means it's set. So that means the value that is stored on this Q is going to be a 1 all the time. If you send a 1 to R reset, that means Q is going to change to 0 and Q prime, which is the opposite side, is going to change to 1. So then here is going to be the 1 and here will be 0. And if you send a 1 1 as an invalid condition, so you don't ever send a 1 1, things just won't work if you do that. So what basically happens is if you look at this as a box, you're going to have a S and you're going to have a R. And then you're going to have a Q and a Q prime. These are not Q, right? So if I wanted to store information and I wanted to store a bit, I would just send a consistent 1 on the set and a 0 on the reset, and then I'll have a 1 here. So now if I take multiple RS flip-flops like this, I have the set, reset, then I have the set, reset. If I set all of them to 1, and I set that to 1, and I set that to 1, I will have the numbers 1, 1, 1, which is basically 7, right? If I set this one to 1, and then I set this one to 0, I'll have 1, 0, 1, which is basically 5. So in a register, when you have a register inside a CPU, what you basically have is a bunch of flip-flops joined together. If you have 4 flip-flops joined together, and you send a set value to each one of them, you'll basically be able to create a 4-bit number. And once that 4-bit number is stored, you can send that to the ALU, and the ALU will be able to process this 4-bit number based on the code. Or like when they do, well, I'll probably do addressing some other time, but this will be like an opcode for addressing function, something like that. So this is the RS flip-flop. A RS flip-flop has two states, set or reset. That means you have 1 on the Q or you have 0 on the Q prime. And most of the times the computer will use what is on the Q as the numbers it looks at to create a number. Right? The diagram fits. You don't need to know the diagram as far as I know from the syllabus, but if they ever do ask you, it's basically either 2 NOT gates, 2 NAND gates, or 2 AND gates. Both of them will do the same thing. What you're really concerned about is the parts here. This is how you store data. Don't worry too much about all this drama you're seeing here. This diagram is just what I lifted from the internet. Any questions? If you're okay, send thumbs up or smile, something like that. Okay, moving on. Alright, so that's the first flip-flop. Next one, okay, a clock signal. Before we go into the other flip-flops, I need you to understand what a clock signal is, which is a series of ones or zeros that come into a circuit. Can flip-flops only output one output? And yeah. If you take, alright. Ariane was asking if flip-flops could output two outputs. Now it's only one output. Just check. Basically, what the computers do is check the Q all the time, and the Q will either be 1 or 0 each time. The Q prime will be used by, I don't know, sometimes it might be used, but basically the Q is what is going to be used to create the number or create the digit that you need. Some circuits will check both Q and Q prime, but there's only two possible outputs, a 1 here or a 0, depending on what your reset choices are. I hope that answers your question. So while you're taking that in, or while the lag taking place. Alright, so a clock signal is a set of ones or zeros. So you could send in a clock signal like this, which will be like 1 0 1 0 1 0 1 0, and every time you get a 1 or a 0, that signal will go into like a flip-flop and it will change the number. So let's say I have a flip-flop and I say I send a clock signal instead of a normal signal, and it's a RS flip-flop, right? And I send on the set, I send in a clock signal of 1 0 1. What's going to happen is that the output, which is Q, is going to be a 1, then it's going to be a 0, and it's going to be a 1. So what that means is if I have a bunch of flip-flops put together like this, I could send a clock signal here, and I could send a clock signal here on the set. I could send a clock signal here on this one. And if I vary the clock signals, what I could end up having is 0 0 0 0. And then I could have, based on the clock signal, I could have this one change into 1 0 0 0 0. Then I could change this one back to 0, and then change this one to 1. And then I could change this to 0, no, to 1, and then change this one to 1. And then all of a sudden, I am counting up like 0 0 0 0, then 0 0 0 1, 0 0 1 0, and 0 0 1 1. And that's how you make a counter. The clock signal will make the counter go up or down depending on how you create it. So let's understand that a clock signal creates the ability to count. If a computer can count, then it could do calculations. Once you could do calculations, then it could do the maths. And once you could do the maths, you could write a program. Because a program is just maths. Okay, next type of flip-flop now is called a D flip-flop. I think there's some past paper question where they ask you to draw this. I cannot remember exactly, but I have the diagram here, so you could check it. The D flip-flop requires a clock signal. So it requires two inputs. It requires a clock signal and the value that I put on D. If the clock signal is at 0, meaning that it is like this all the time, 0, 0, 0, 0, 0, and the D is 0, the Q and the Q prime don't change. They stay, well, however. If the clock signal is at 0 and D is at 1, the Q and the Q prime don't change. So basically, the point of a D flip-flop is, well, not the point of a D flip-flop, but how D flip-flop works is once the clock signal is at 0, nothing changes. However, if the clock signal jumps and becomes a 1 at any point in time, then the D flip-flop is going to react. So when the clock signal is 1 and the D is 0, Q is going to be 0. When the clock signal is at 1 and D is at 1, Q is going to be 1. So basically, a D flip-flop responds to the clock signal. So when the clock signal is at 0, your Q is 0. When the clock signal is at 1, Q is 1. So you could modify the output of 1s and 0s by varying the clock signal. So this flip-flop is better than the RS because in the RS you have to manually set the values. But with a D flip-flop, you don't have to manually set it. You can let the clock do the changing for you, and it just make the clock either stay at 0 or 1, depending on how it goes. Right? Just assume that the clock could manufacture its own 1s and 0s by itself. So the power of a D flip-flop is actually the clock. When the clock is 1, and D is 0, 0, and D is 1 and the clock is 1, yeah, 1. But it must be in line with the clock. CP here stands for clock pulse. But remember, all this thing really doing is counting up or down. Why is it counting up or down? Because inside the register, you need to have numbers, and these numbers have to change. Any questions? If you're good, say you're good. Say okay. Or ask a question. All right, we good? Great. All right, moving on now. Last flip-flop now. JK flip-flop. This is the one that most computers use, and this is the most what's the word? It's the most versatile one out of all of them because it has a J, it has a K, and it has a clock. So actually what J and K stand for, I can't remember right now, but that doesn't matter. When you get to some university program, that'll probably matter. But you see that there's a Q and there's a Q prime for sure. So it depends on the clock pulse, meaning the clock pulse have to be a 1. If the clock pulse is a 1 and you set J to 0 and K to 0, that means it's not going to have any change. No change is good when you want to store stuff. If you want Q to constantly be a 1 all the time, because you need to store the memory temporarily, or like you need to store the memory for future use, that means Q will always be a 1. So you could set J to 0 and K to 0, and the clock will stay at 1, and it will always work. If, however, you want it to change, then you leave j as 0. If you want it to be a 0, you send j to 0, k as 1, and you'll get 0 or 1. So the q will be 0. So you set j to 0. If you set j to 1, your q will be 1, which is good. So we have the ability to manipulate q because q is always our friend. Q is where we store numbers. If we could store numbers, then we're good to go. But look at the cool part here. The cool thing is when you send a 1 and a 1, it's going to automatically switch. So q is going to change from 1 to 0, and q prime will change to 1. If it's on a 1 and a 0, it will flip again. And the toggling is what makes addition very easy. Because addition now, it basically means if you want to add numbers in, carry out numbers in binary, you're going to send no toggle here, no toggle here, no toggle here, toggle this one here, which will be 1. Then you're going to say no toggle there, no toggle there, toggle here, which will be 1, and toggle here, which will be 0. And then we're going to add again 0, 0, no toggle, toggle that one, and you get 1, 1. And then you could keep counting up. Once you could count up, then you have the ability to keep track of things, you have the ability to do counters, you have the ability to do all kind of things. Because the whole point of a flip-flop is to store memory, store information. And once you could store the information and manipulate it, you'll be able to do calculations, which is basically how binary calculations take place. But what happens is that these flip-flops work together to get this stuff done. So the theory behind the flip-flops is simple. A single flip-flop could be used to store 1 bit or a binary digit, right, of data, which I explained already. So basically the q is going to be the 1 or 0. Any one of the flip-flop types could be used to build any of the others, so you could combine flip-flops. I don't know if you notice inside here is a RS flip-flop, and when you join the RS flip-flop with another one, you could work at, like, create different circuits inside of it. Data contained in flip-flops could represent the state of a sequencer. Remember, a sequencer is like number counting, the value of a counter, which is adding the counter, or a character in the computer's memory, or a piece of information. So several flip-flops, when you put them together, could keep numbers for you. So if I have one flip-flop here, one flip-flop here, one flip-flop here, next one here, it doesn't matter if this one is a JK, this one is a RS, this one is a D, and this one is a JK again. What matters is the Q value that comes out of here is going to be manipulated so that I have digits that I could use, which is like 0, 0, 1, 0. If I want to represent a number, all I have to do is chain some flip-flops together. For lack of a better word, I chain them up like this. And once they chain together and I have the appropriate input or whatnot, coming from wherever it is, I can make numbers. And once you can make numbers, you can get a computer to do calculations because the ALU will be able to do the maths, which is why you learn all the binary calculations. All the binary calculations that we learn, which is like dividing by 2 and hexadecimals and all that stuff, it comes down to these circuits holding 1s and 0s. And once these circuits hold these 1s and 0s, you should be good. And that is how flip-flops work from the logic. Ask away while I drink some water. But like a pass paper question, I just Flip. No questions? Alright, so look at this question here from 2011. What is meant by the term flip-flop? Yeah, you don't even have to know any diagrams or anything like that. A flip-flop is, where do I have it? A flip-flop is a digital circuit that has two stable states. Answer. Let's see what other flip-flop question we had. Give two properties of a flip-flop and state one use of this device. Properties, it holds ones and zeros that have a set and a reset, and one use is to create a register, which I have said here. To create a sequencer, a counter, register. Let's see what else they ask about flip-flops. Draw a diagram to show a set of flip-flops could be create a 4-bit register. Well, I showed you that here. Anything else? Nope, that's it for flip-flops there. So, should be good to go there. And I am glad to be of service. Alright, remember, online classes available from size on Tuesday, upper sixes Tuesday night, lower sixes Thursday. IT is Wednesday night, and lower sixes. Follow on Instagram every night on a Sunday from 9 to 10. It's YouTube Live, and you are welcome. All right, bye bye.